We study X14NQ. This is for the students who are not familiar with X14Q. So it is for preview. So if you understand the X14Q without any problem, you don't have to watch this video. A bit of mass m at point P is constrained to move around the circle of radius r without friction in a vertical plane under the constant gravitational acceleration, and unit vector E1 hat and E2 are given in here. Discuss the rotational motion of the particle. X, position vector, X is like that, and ER, unit vector, unit radial vector. E theta is perpendicular, unit tangent vector, unit tangential vector. ER and E theta. The axis of rotation, so it's making a rotation. However, because of the gravitational acceleration, this motion is not a uniform circular motion. It is a non-uniform circular motion. Anyway, it is making a rotation with a variable angular velocity, and axis of rotation is at least fixed, that is along the z-axis. Depending on the rotation, if it is rotating counterclockwise, then the angular velocity is positive. If it is rotating clockwise, then the angular velocity is negative. The position of the particle can be expressed like that. Here, this is a unit radial vector on the xy plane. We have expressed this position vector as a linear combination of the two Cartesian unit basis vector. The merit of using Cartesian unit basis vector is EI dot EJ equals Kronecker delta. It is 0 if I is not equal to J, if it is 1 if I equals J. As you know, X and Y axis are perpendicular to each other. X and Z axis are perpendicular to each other. Therefore, they are the directional cosines. A cosine half of pi, exactly 0. We express this x vector as a linear combination that is a parallel to the axis of rotation and perpendicular component that is perpendicular to the axis of rotation. Because we can also say E2 dot E3. That is also 0. So because of this, 1 and 2 components are all perpendicular to the axis of rotation. X parallel, that is a parallel to the axis of rotation, vanishes. Hence the lever arm vector, this is called the lever arm vector, representing the perpendicular distance and the direction from the axis of rotation. This is nothing but the x vector itself. If I square this lever arm vector, it is very useful to understand the rotational inertia, because mass times x perp squared is the rotational inertia or momentum inertia. The square of x perp can be computed by taking the scalar product of itself. R radial vector, R radial vector. I can make use of this relation directly, but for the students who are not familiar with the radial and tangential vector, I can make use of the expansion as a linear combination of a unit Cartesian basis vector E1 and E2. We expand the scalar product E1 dot E1 cosine squared, E1 dot E2 cosine sine, E2 dot E1 sine cosine, and E2 dot E2 sine squared. By making use of the multiplication table for this unit's Cartesian basis vector scalar product, 1 1 equals 1, 1 2 2 1 they are 0, and 2 2 is 1. Therefore, these two terms survive and these two vanishes. As a result, this is nothing but r squared cosine squared theta plus sine squared theta, and using Pythagoras theorem, it is r squared. So x perp squared is r squared, that is constant. The rotational inertia of the particle is now obtained as, regardless of the position of the particle, depending on the angle theta, we always have a constant radius squared, that is the square of the lever arm vector. Okay, the sum, because it is a point mass, the integral is trivial, the mass itself. So moment of inertia is mr squared. Next we consider r dot. R dot is trivial, is a 0. Now r is a constant. Time derivative of unit radial vector can be computed in such a manner. Er is expanded as a linear combination of two Cartesian basis vectors that are independent of time. So only the time dependence appears in cosine and sine. We can make use of chain rule because theta is a function of time. So derivative with respect to time can be made by taking the angle derivative first and then multiply the time derivative of the angle. And we know the derivative of cosine is minus sine, and derivative of sine is cosine. As a result, I replace this time derivative with theta dot to find that time derivative of unit radial vector is theta dot multiplied by the unit tangential vector. Now we are interested in the velocity of the particle. Velocity of the particle is time derivative of position vector. Position vector has a constant radius in this case, so time derivative of radius vanishes. And so this one we ignore. And then r is factored out, and time derivative of unit radial vector, and this one we just have obtained theta dot e theta hat. As a result, the linear momentum of the particle is a mass times velocity, and velocity of the particle depends only on the unit tangential vector, and that is mr theta dot. But you must remember that theta dot is not constant. It is not a uniform circular motion. Alright, must memorize the following multiplication table for the cross products. any cross product of a parallel vector A cross A equals to 0. We substitute E1 hat, E2 hat, E3 hat. In any case, if they are the same, the cross product is always a 0. Next, we compute the scale of a cross product of two vectors A cross B, that is magnitude of A, magnitude of B, sine theta, where theta is the angle between A and B, multiplied by the unit vector. If they are not collinear, they always make a plane, and n hat is perpendicular to that plane. There are two possibilities of this direction, but we choose only a single one that can be obtained by rotating A to B counterclockwise. In here, not this direction, but this direction. That is, there are two angles making 360 degrees along the direction with a smaller angle. So then, if I rotate counterclockwise, the positive z-axis direction is the unit normal vector. So there is no ambiguity. Because of this relation, if I exchange A and B, the direction of the normal vector is upside down. So E1 cross E2. In the three-dimensional case, E1, E2, E3. 1 cross 2 is plus. 2 cross 1 is the same as E3, but negative sign. 2 cross 3 equals 1. 3 cross 2 should be 1, but with negative sign. 3 cross 1 equals 2. 1 cross 3 is minus 2. We also say these can be expressed E1 hat, EI hat cross EJ hat X equals sum over K that runs from 1 to 3 epsilon IJK EK hat, where epsilon IJK is a Leibniz-Civita tensor when 1, 2, 3, 2, 3, 1, 3, 1, 2. Then we say it is an even permutation. Even permutation. 2, 1, 3. Exchange these two. 3, 2, 1. 1, 3, 2. We say they are odd permutation. When IJK construct an even permutation of 1, 2, 3, odd permutation of 1, 2, 3, we allocate plus 1 and minus 1. Except that among 3 times 3 times 3, 27 cases, 21 cases disappear, everything is a 0. These 3 permutations will give plus 1, and these 3 odd permutation will give minus 1. Okay, so 3 times 2 times 1 is a 6 permutation. Among the 6 permutations, we have a 3 even permutation giving epsilon ijk equals a +1, and 3 odd permutations giving epsilon ijk equals -1. In a similar manner, just like 1, 2, 3, we still have the same relationship among ER, E theta, and EZ, the E3. So this one, although their directions are different, their relative relation, this relative relation, and this relative relation, they are equivalent. Again, ER cross ER, same thing. E theta, same thing. E3, E3, their cross products are always 0. What about the case of ER cross E theta? ER is E1 cosine, E2 sine. E theta, E1 minus a sine, and E2 cosine. The cross product of ER and E theta can be expanded as a cross products in terms of cross products VI and EJ. 1 minus a cosine sine, 1 2 cosine squared, 2 minus 1 minus the sine squared, 2 sine cosine. As you know, same thing disappears. Different, let's see, it is even permutation. 1, 2, then the answer is 3. 2, 1, this is odd permutation. Therefore, 2 cross 1 equals a minus E3. Therefore, if I make use of the fact that same thing disappears, then we obtain E3 cosine squared and sine squared. According to Pythagoras' theorem, it is E3. It is just like the case E1 cross E2 equals E3. We have ER, E theta, E3. That's the reason why I have told you they have a consistent relationship. Okay. Still, if I exchange the order, I have negative sign. Remember. We recall that the momentum inertia of the particle about E3 is mass times radius squared in this problem. Orbital angular momentum is x cross p. X is radius multiplied by the unit radial vector, and momentum is mr theta dot unit tangential vector. We have mr squared theta dot and then er cross e theta. And as we just have seen, it is E3 hat. In addition, mass times radius squared is the moment of inertia of this system. Therefore, it can be expressed as a moment of inertia I multiplied by the angular velocity. And the direction is along the positive z-axis. When this theta dot is positive, that is rotating counterclockwise, this angular momentum is parallel to E3. When the angular momentum, when the angular velocity is negative, that means it rotates clockwise. Then the orbital angular momentum of this speed is along the negative z-axis. That's it.